Okay, this post was made like over 8 years ago, but I had a student who asked me if I could help her with it. So here we go. Here's the function. It's a rational function, a polynomial divided by another polynomial. Here's some guidelines for graphing a rational function. Uh, these are the basics right here. There's some more stuff that you can do. You can check to see whether the graph contains a hole, which we're going to check on the next board. You can check for an oblique or slant asymptote. And if you're using calculus, you can check for relative maximums or minimums using the first derivative test, and you can check for points of inflection, test for concavity by finding the second derivative. So here's a summary of all of those. Crossing points, we're checking to see if the graph of the function crosses its horizontal or its slant asymptote. The graph of a function can never cross its vertical asymptote. Okay, so here we go. Here's the original function. And let's factor that. The numerator we can factor by grouping into x cubed minus 1 times the quantity x minus 2. The denominator, we can factor out the GCF and then factor x squared minus 4 as a difference of squares. And the whole point is that these x minus 2's cancel out. So there's a hole at x equals 2. And there's where the hole appears at the point 2 comma 7/8. Now, if you factor I use the letter R here as for the residual function. That's the function you get after you cross out the factors that create the hole. This numerator factors as a difference of cubes. The denominator, of course, we can still factor out the x, and the x minus 2's have canceled. But now, when the degree of the numerator is 1 greater than the degree of the denominator, you can get a linear, oblique, or slant asymptote and check out what it is by doing long polynomial division. And here's the result. This function definition is the same as this. If you graph them both, you get the same exact picture, but you can tell a little bit more about the function sometimes when it's written this way. Basically, it's because as x approaches infinity, this term goes towards 0 because the degree of the denominator is greater than the degree of the numerator. So the denominator overwhelms the numerator. So this guy right here is the slant asymptote. Y equals the x minus 2. We'll see that. Board 3, let's start identifying the points and asymptotes that's going to exist on the curve. The x-intercept is found when y equals 0, and y equals 0 when the numerator equals 0. So here's the numerator. You can look at either one of these. This should be an x here. This will never equal 0 unless we're talking about imaginary numbers. But when x equals 1, we do get an x-intercept at 1 comma 0. The y-intercept exists when x equals 0, but r of 0 is undefined because we get 0 in the denominator. Vertical asymptotes happen when the denominator equals 0. That's at x equals 0 or x equals -2. For horizontal asymptotes, there's 3 cases. When the degree of the denominator is greater than the degree of the numerator, then y equals 0 is the horizontal asymptote. When the degree of the denominator equals the degree of the numerator, y equals the coefficient of the highest degree terms. we won't look at a specific example of that. But here's our case. When the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. End behavior. Notice what happens here as x approaches infinity. This term goes to 0. If x is approaching negative infinity, this term, or those two terms, are approaching negative infinity. So the end behavior is down to the left. As x approaches infinity, this term goes to 0, and x minus 2 goes to positive infinity. So we say the end behavior is down up. And the linear slant asymptote, we found the equation on the previous board, y equals x minus 2. Crossing points, does the graph cross its horizontal or slant asymptote? Of course, for our problem, we only have a slant asymptote. Here's the rule for the residual function. Here's the rule for the slant asymptote. Are these two ever equal? Well, of course, the x and the minus 2 cancel out, giving us a 0 over here. Does this ever equal 0? It does when the numerator equals 0. So when x equals 1/4, indeed, the original function crosses its slant asymptote. Here's the arithmetic for finding the y value. There is a crossing point, 1/4, -7/4. Now for calculus, this is horrible. Here's the original function. You could use the product of the quotient rule to find the first derivative. I won't go through all the details, but there's simplified form. The first derivative is undefined at x equals -2 and x equals 0. That's not surprising because that's where the vertical asymptotes occur. But the first derivative equals 0 when the numerator equals 0. We want to test for critical numbers. And to solve this equation, you're probably going to have to use numerical methods. And here's some examples of using Newton's method to find out when this function equals 0. Turns out at about -4.09, the first derivative is equal to 0. And also at -0.612 is equal to 0. So here's a picture of the first derivative test. Oh, this -4 is approximate. This -0.6 is approximate. There's vertical asymptotes at -2 and at 0. So those are going to create branches on the curve, but we still want to find out what happens in each separate branch. So to the left of this -4, turns out the first derivative is positive. So the original function is increasing. To the right of -4, like at -3, the first derivative is negative. And that means we have a relative maximum at this -4.09. For the branch between -2 and 0, we do have a critical number right here at -0.6. To the left of -0.6, the first derivative is negative. So the original function how can that be? Oh yeah, the original function is decreasing, and to the right of -0.6 at -0.5, the first derivative is positive, so the original function is increasing. So we do go from decreasing to increasing, and we have a relative minimum in here. And these are approximate values for the y values at the relative max and min. Okay. On board 6, test for concavity. Wow. I would square this binomial before I tried to use the quotient rule, but it's very tedious. But after you apply the quotient rule and simplify, this is what you get for the second derivative. And y double prime is still undefined at the vertical asymptotes, but it equals 0 when the numerator equals 0. Again, applying numerical methods, I divided every term by 2 before I started. Turns out that at 1.85, the numerator of the second derivative is 0, and so we can apply the test for concavity. They're the vertical asymptotes. To the right of 0, there's this hypercritical number. Concavity might change there, and the table shows that it does. To the left of -2, the second derivative is negative, so we think frown because of negative, concave down. Between -2 and 0, like at -1, the second derivative is positive, so concave up. To the right of 0, we have to check between 1.85 and 0, and to the right of 1.85. So 1.5 has a negative second derivative, concave down. To the right of 1.85, second derivative is positive, concave up. Since the concavity changed, there's a point of inflection at 1.85. And actually the y value is 3/4. Okay, so what have we got so far? Summary before we try to sketch the curve. There's the x-intercept at 1, 0. There are no y-intercepts. This green dashed line to the right is actually the y-axis. There are no horizontal asymptotes. This blue dashed line is the slant asymptote. There's the crossing point. Relative max is right down here. Relative min is right here. Point of inflection right there. And there's the hole. Okay, so this allows you to start sketching the curve. As for the branch to the left of the green dashed line, the left green dashed line, this is a relative maximum. So the curve must be going down here. And as it approaches its vertical asymptote from the left, it approaches negative infinity. As we go this way, that graph is going to get closer and closer to its slant asymptote. It's never going to touch it because the only point where it touches is up here. Up in this branch between green dashed lines, this point's a relative minimum. So we must be going up this way and up this way. Whoop. And again, the graph can never cross its vertical asymptote. And finally, to the right of the right green dashed line, right vertical asymptote, we know the graph crosses here. It's got to go up this way and pass through these points. Then it starts getting closer and closer to its slant asymptote. And of course, it's coming down this way. There's the sketch. It's hard to tell if this is a point of inflection. The curve actually just starts at becoming concave up at that point. It's very hard to tell looking at the graph. Here's a table that kind of shows you how to graph this function. Remember, the graph of a function never crosses a vertical asymptote, so that means we've got to have 3 branches. As x approaches a vertical asymptote, the y value goes to either infinity or negative infinity. So as we come in with x values getting closer and closer to -2 from the right, you could test values, but we know that this is a relative minimum. So it's got to be going up to the left and up to the right. Okay, there you go. Hope that gave you some idea of all the steps you can go through to graph a rational function. course, you can just use a graphing calculator or the Desmos online graphing calculator to type in the function, and that'll give you a clue as to whether you've got it right or not. There you go. Hope that helped, Sally. And if you have any questions, post a comment.